part of the infrastructure group at IBM. And the number one question I'm getting is, why are you still in infrastructure? Everything is AI, agents, cloud, AI agents, and more AI, right? Well, infrastructure is still key. And I want to talk to you about these three things on why infrastructure is actually our foundational IT that supports everything else that we're doing. So first, real short about why infrastructure. Let me ask you a question. On average, how many times a day do you think you're touched by IBM technology? IBM infrastructure in particular. Any guesses besides the IBMers?
Each minute.
Each minute. How many times? It's 30. Exactly. That's also one, right? It's 35. So if you do a transaction, if you do a booking, if you do whatever, on the back, there's an IBM infrastructure technology making that transaction or that booking happen. And that's all infrastructure from IBM, right? You all know mainframes, so our 90% of our top banking customers are still running mainframe year to day. So why is infrastructure, right? So if you look into the past, how many years, every 50 years there's a new revolution. So starting at the 1700s, you have the industrial, you have steel, electricity, age. So what age are we now living in? A few years ago we had this weird virus, I'm not sure if you guys remember that. So are we at the age of health, right, with all the virusing, or are we at the age of sustainability? So the real question is, where is infrastructure in all this, right? So first, data. And I'm not talking about boxes of data, I'm talking about actually storage. So we as man or humankind, I should say, are expecting to produce 175 zettabytes today. We can basically categorize that into two ways. We have structured data, which is like database tables, and unstructured data. If you use your phone and you take a picture, your average resolution is already like 180p. So on average, a picture was like 12 megabytes. 2 years ago, this picture was a few kilobytes. Right? Our resolutions are getting bigger, so also our data is exploding on that. So I am thinking in visualization, right? So how does this look? Does anybody of you know what this is? I did this a few weeks ago at a university. I had no idea. Right, so this is a CD-ROM. Does anybody know how much data you can store on a CD-ROM? 750, right? And it's like 1.44 millimeters thick. So now the question is, how many of these do you need to store 175 zettabytes? Any idea? Besides a lot. So if you do the math, then you actually need 290 million kilometers to be stacked CDs. That's from Earth to the Sun and back. That's how much of data we are generating as mankind, right? So one thing that we use, and I'm sure you all know what this is, of course. It's a tape library, exactly. So all the big players out there that gather this data are using tape because it's still the most cheapest media if you don't use it or store data on it. So all the hyperscalers, so if you store something on OneDrive, this is the technology that's being used. Microsoft is our big customers who are using it. If you search for an old YouTube video, you're getting like a shitty resolution the first 5 seconds. That is a tape library from IBM at the back, grabbing a tape, loading it into the drive, and then it pops up at 720 or 180. So IBM tape is really, in terms of storing data, still out there for this 175 zettabytes. The second part of infrastructure is compute. So if you look at the 8 pictures I showed at the beginning, the last one was my new PC. So my new PC has the equivalent of a mouse brain. So I have to give it 1,000 pictures of a cat, and then the first picture after the 1,000, he can say like, yeah, this is a cat with 99%. Right? So the real question is, if you look into the history, IBM is doing this compute for a long time, right? And right now we have the equivalent of a human brain. When do we become Skynet, right? So when that CPU or AI becomes self-aware, travel back in time and change Watson to Skynet. That's pretty much it. But all jokes aside, singularity, so when compute can think faster than a human, it's coming. It's not just futuristic stuff. If you look into our compute track in terms of power already, we're getting close to that, right? So I made this presentation on infrastructure, because if I talk about infrastructure, I always talk about bottlenecks. That's the only thing that we are trying to solve for our customers in our workloads out there. So if you look at these bottlenecks, I can basically say that it's measured in terms of an I/O tag. How long does it take for my data to be computed, to be calculated, and sent back to the user? So you can categorize it in 3 different ways. So you have the software, you have compute, and you have storage. So if we first look at the software part of this stuff, right? Also at the picture at the beginning, you saw that I had 3 kids, 3, yes. They all have tablets. So if they're playing on their tablets and the tablet is breaking down because of battery issues or they drop it, they just steal my tablet. They log back in and they continue where they left off. That's basically also requiring a new way of infrastructure, right? Today, if I look at customers who are running VMware or Microsoft installations, I call it the click generation. If you install something, you do next, continue, complete, and you're done. The generation prior to that is using this TN3270 thermals hooked up to a mainframe. So the new way of doing infrastructure also expects new ways of doing that kind of business. So how does that look like? So I'm a techie, so I'm sorry if I get a little bit too technical, but if I draw a legacy picture of infrastructure and I close my eyes and I think about the most important part of the infrastructure, storage, right? Without data, you're nothing. So on top of that, there's a SAN, there's a network, then you have your compute host. It's probably running like VMware or any other virtualization engine. On top of that are your virtual machines, and there sits the application. So from an IBM point of view, our customers, 95% of those are still running this kind of environment. I'm not calling it legacy, I'm calling it foundational IT. A few years ago, we did an acquisition, a small one, called Red Hat. Red Hat has a product called OpenShift, which is a container management platform, but it still needs to run on somewhere, right? The cloud is just someone else's infrastructure. Just as this new layer of doing business with Kubernetes still needs compute to be run. So this can be x86, it can also be Linux 1, which is basically, I'm about to say this, a mini mainframe. So it can also run on IBM Power. But it can also run in the cloud, right? It doesn't really matter where it's at. So on top of that, you have your new cool AI stuff, your new machine learning, your deep learning, all the stuff that you can grab on the internet and deploy on this layer. So a lot of our customers are doing app remanufacturing, as they call it. So they're trying to get this legacy environment with this application migrated to this side of the world. That is a hard thing to do. So at IBM, we had a product called Same Time. I'm not sure if you guys know that. It's a really old legacy chat program based in Lotus Notes. So we switched to Slack. Slack is a containerized application. So all of a sudden they got a few million extra users, so they set up a lot of extra containers to facilitate those connections. So not just app remanufacturing, but also customers and end users are looking at different workloads that easily deploy. So how do you start off with that instead of doing a whole transition? We say start off with the storage. Your storage needs to be available in both the new world and the old world. So I'm Dutch. One of the pictures was with an orange thingy, so I'm from the Netherlands. We are known as cheapskates. I'm just going to say it out loud. I'm sorry, Claudia. So what we do if we go out and the guy or girl at our table is using a little bit more than we agreed upon, I'm going to send him or her a ticket, which is basically asking for a little bit of extra money. So this application is sitting on this new way of thinking. And one of the things you can do is you can say, yeah, thank you GIF, so that if you pay the 25 cents that I'm asking extra because you order, I don't know, mayonnaise or for some reason, it's being spun up and being seen by everybody. Right? If I send this to the whole of you to ask for €1 per person attending this session, there's more containers to be spun up because everybody tries to look at the same GIF file, right? But even if you pay, there still needs to be a legacy update on this system saying minus €1 from this account plus €1 on this account. And this is the hybrid clouds that we're trying to build, that our customers are building. So it's getting the basic environment, the legacy IT, towards this new world. So one of the things that IBM is using is because how do you build this new environment, right? You need all skills, you need a lot of things. So we put a box around that and we call it IBM Fusion. So Fusion is what we call an AI factory or OpenShift in a box. It's a black box appliance, and you basically are not just using software-defined storage, but you can also store your VMs. So a lot of our customers are complaining about VMware, the Broadcom, and price increase. This could be one solution for them, right? And we see our business partners are making plays around this on how to migrate from a legacy VMware environment to this new world. IBM Fusion. So that is the software part, right? Where we are fixing a lot of HCH for it. So the next part is on compute. Anybody has any idea what this is? Of course, it's a CPU, right? As a matter of fact, this is an IBM Power CPU. And Power is known for its Rust features. We have like reliability, availability, and serviceability. So the other questions I'm getting is like, okay, what is your system differ than, I don't know, an Intel who is half the price? So I'm not going into technicalities, but what we see happening is that, for example, if you look at the NSA, they have something on Mars called the Mars rover. They placed a really old Power CPU in that. And why did they not choose the latest technology or the latest Intel chip? Because Power has proven itself to be stable for the last 100 years. So if you send something to the moon, you cannot easily do maintenance of that, right? So they sent the Mars rover up to there with IBM Power chip. It's really good at the lower level of storage, so it can do databases really well, really fast. So the NSA is using it. I'm not sure who owns a Nintendo, I'm a bit of a gamer. So in the old Nintendo consoles, there was actually an IBM CPU. So with this new compute, which is getting denser and denser, and we're going to announce the Power 11 somewhere on the holiday, right? We're getting there. But now, the most important part, storage. Same question, what is this? Hard drive, right? Same when I asked in university, nobody had any idea. This is actually a spinning hard drive. You know, the cheaper models, they stand at 7,200 RPM, and there was like a hat like moved around. So this is like a legacy way of doing storage, right? So at the beginning in time, we had controls, and we were talking about an average latency of 10 microseconds. So it took 10 microseconds to get the data to the CPU and back to the data. And that is because, you know, the Ethernet base had to travel on the CPU, then HBA with memory, and then it had a backend bus. So a few years ago, we had this, SSDs, right? Solid state. And what we saw happening is a factor of 10 lower latency. But still, we had the problem of traveling over a CPU and over a chip back into a backend. So in terms of bottlenecks, this was not a bottleneck. This became a bottleneck, right? The compute layer. So half a year ago, we did something else, NVMe. And now we have a system that is completely separate of CPU and adapters and can talk directly to the storage with another factor of 10 latency. So this happened, I don't know, a few years ago. We moved on really fast towards this and even faster towards this kind of solutions. So in terms of IT and bottleneck, infrastructure is making sure that the data is like fast and flexible. This is already part of our IBM portfolio. We have IBM flash systems. We actually have one on the booth, an entry model, so you can actually check it out. So it's part of our main portfolio, and these already has the flash core modules, so the new NVMe drives attached to that. So that is the storage part, so lowering the I/O path. Now what's next? The reason why you're all here, right? If I look into the history of IBM, and I get a lot of questions on AI, AI is nothing new. We did, where is it? Somewhere with no language understanding, right? The chess, we already defeated by chess. That's a form of AI. We just had more compute and more data in order to beat the chess master. We also had to do a lot of data in order to understand language with Jeopardy, the game host show in the US. So that was all about data. Right now, we're talking about qubits, right? Anybody has any idea? This is a quantum computer, right? Our quantum system. So, not to get into too much details, but it consists of 3 platters. And the lower platter is 0.3 millikelvin in terms of temperature. That's colder than outer space, right? So we're trying to make the molecules as slow as possible so we can influence them, right? So why is this important, right? A classical computer consists of 1 and 0. It's on or off. This is how we are doing compute. Quantum computers can have a so-called superposition. And if you read a superposition, it can be a 1 and a 0 or a 1 and a 0 at the same time. So you have multiple states. And that means that instead of doing classical calculation, where you have to have like 4 bits to do a simple calculation, you can do it with 1 bit, 1 qubit is called a quantum bit. So you can do more computations with the same amount of energy spent. Anybody know Schrödinger's cat? Right, so the question is like, okay, so I can't talk bullshit, I'm sorry. So basically what a superposition is Schrödinger's cat did a test where they put a cat in a box and they also put a little bit of poison in the box. Then they closed the box. So the way that you have to calculate is that the cat is or alive or dead, so two positions. And unless you open the box and you observe the quantum state, then you know if it's dead or alive. So we in quantum do chemical computations based on this way of calculating. So we're both assuming it's alive and dead, so 1 and 0 at the same time. So how does this mean and how does this work? Because I'm not a physicist, so I created like a small video game on what quantum actually is. So let's say we as mankind are being placed on a map and we don't have any compute. So pre-historical data, we were placed on a map, we had no computers, so we had to walk around, right? We had to discover our map of the life around us. We could interact with each other to understand like, hey, there's another tree, but we didn't have the computational power to build a bridge, so we couldn't explore our entire island. So then we invented the IT area, so this is all IBM, there's still place online, as you probably know. So then we invented IT, so we could build bridges, we had roads, we could ride horses, so we could explore more of our mathematical life lab. But we still had areas where we could not go, we could not climb the house, right? So then you get the IT bubble, so the computer became faster. This is the hype that I showed at the beginning, where we're now the equivalent of a mouse brain. So we basically unlocked our entire map of humankind from the ways that we explore everything. So the big question is, what is then quantum? Right? Is quantum a faster car to travel around or an airplane? No, it's more a boat, right? So we place it in waters and we're going to explore territories that we have no idea on what we're going to see or what's going to happen. So with this other type of computing power or computing data, we're going to explore our complete human map of what else is out there. So one of the things that's interesting, and like I said, I'm not a quantum physicist, but we do a lot of research at IBM. So one of the studies that we did was around this. So this is the algorithm to crack RSA. RSA is what you use on average if you talk to your bank. You open your banking app on your phone, you talk to your bank and you want to see the status. It's using this type of encryption, RSA. So this study is showing that with 20,000 qubits, if you have a system that's 20,000 qubits strong, you can crack that with 8 hours. In 8 hours. Right? So it's not that you share your public key, your private key. No, we just look at your data and we can crack it. And if you want to read the full article, which is 250 pages with a lot of these, feel free. This is not something that is futuristic. This is the roadmap of IBM Quantum. Everything in green we already are deploying. So right now we're already on this area. So if you zoom in on that, I think we already have the 133 qubit is live, but the 5K gates and the 165, which makes up to 1,000 qubits, is already running in production at some of our customers. It's not 20K, it's 1K. So if you multiply 8 by 1K, you get there, right? So it's not a matter of how, it's a matter of when. So, what do we do against that? If you look again at storage, so we are the only one who's using crystal cryptography, which is basically meaning that it's quantum safe. So all communication that is done on this storage system, in cooperation with our power, the 11 announcement, and also in our mainframe, is already quantum safe. It's unable to fail. You cannot use Shor's algorithm to find prime numbers using this type of technology. So the question is steal now, decrypt later, right? Hackers usually are already inside companies before us even discovering this. They're already looking at our data, and the thing that they cannot decrypt, they steal, they store, they wait for the quantum system to be available in a few years, and then they can decrypt it. So it's thinking of, okay, that's interesting. If I look into ransomware attacks, because we get also a lot of questions on that, I basically ask the customers one question. Would you rather pay in Bitcoins, or would you pay in euros? Because again, it's not a matter of how you will be attacked. It's It's a matter of when you will be attacked. And there's a lot of cyber threats already out there today. There's tons of examples of ransomware. Our good friends from HDS got ransomware two weeks ago. I'm sure if you guys know that. Their complete facility went down. NKB companies or mid-range companies who are being cyber attacked with ransomware don't survive. 80% of them had to close all of their doors. So this is a really key opening to talk about our customers in terms of what do you look for? What do you want? What's next? So quantum is going to get us to the next step. Does anybody know the Kardashian scale? Ah, okay. The students did a little bit more to know about that. So it's a matter of how do we measure a civilization, right? So if you're on a scale of 1, then you utilize all your energy from your own planet. So right now, we as mankind, or humankind I should say, are at 0.75 because we consume 17 microton of energy every single second. If you're at a scale of 2, then you harvest the sun's energy in our case. So you build like a Dyson sphere. This is all like futuristic stuff, right? So quantum is going to help us increase this scale, right? By doing research in terms of nature, in terms of our DNA, in terms of everything that we don't know yet is out there. That's the boat that's going to explore the underwater sport, right? So quantum is going to help us with that. So, final question for you guys. In what age are we going to live? What's the coming 50 years going to be looking like? Infrastructure. It's all about infrastructure. I mean, everybody's talking about AI and agents, but it's the age of infrastructure. Because you can do all the computational new cool workloads that you want, the infrastructure needs to be supportive of that, right? Remember the iPad example? Your infrastructure needs to support that. So it starts with the infrastructure, and then we go all the way up. Now, small quiz. Anybody know the temperature? 50. I lied. Right. That's pretty much it. Any questions? All right. Thank you, guys.